Welcome to my talk on how not to die young, lessons from cardiovascular engineering. So, we live at a time when 33% of all global deaths happen due to cardiovascular diseases, of which 3/4 happens to low to middle income countries such as India, accounting to almost 18.6 million deaths worldwide, of which 6.2 million are premature. That means you are dying within the age 30 and 60. So, why does this happen? What are we missing and how not to die young? So, this is the premise of today's talk. So, let's start with the first question. Why does this happen? So, you might look young, seem healthy and fit outside, but that need not be always the case inside. Your chronological age is different from your vascular age. So, in true sense of aging, you are only as old as your arteries really are. So, what are we missing that this keeps the mortality rate keeps rising? So, traditional risk factors, it could be the cholesterol in your blood or visually identifiable factors such as obesity. It takes time to mature enough to be detectable either in blood or as a visual identifiable factor. So, traditional risk factor fail to predict cardiovascular disease in time so that you can take the corrective actions, whether it could be lifestyle modifications or medications. So, how not to die young comes to my final question, and welcome to lessons from cardiovascular engineering. So, the lesson number 1 that I want you guys to remember is that the arterial pulse wave is a traveling wave. So, just like any mechanical waves, maybe the sound that I generate from my vocal cord, which is the source, and the air acts as a medium. So, you need a source, you need a medium for mechanical waves. So, in the arterial network, the heart acts as the pulsatile pump, the energy source, and the extensive network of blood vessels, elastic in nature, acts as your medium. And together they produce the arterial pulse wave, which has characteristic valleys and characteristic peaks for you to take a look at. So, the arterial pulse wave is a signature of an individual's vascular health, because any perturbations either from the source side or from the medium side will get manifested in the arterial pulse wave. Now, let us take a look at life cycle of a cardiovascular event which eventually results in a heart attack or a stroke, represented here as cross sections of your blood vessels getting accumulated with plaque over the years. Now, if you really wanted to detect the early manifestations of cardiovascular disease, where you have to look at is the artery vessel wall itself. Any degradation on the vessel wall material property, which is nothing but the medium of pulse travel, is of paramount importance to us. Now, we call this as increase in the vessel wall stiffness with aging. Now, let us take a look at the artery vessel wall itself. So, it is characterized by a nonlinear stress strain curve. Now, any degradation of the blood vessels wall's material property, as you might recall, gets manifested in the arterial pulse wave. Now, all we need perhaps to measure an early manifestation of cardiovascular disease is to measure some measurable property of the arterial pulse wave that can preserve the nonlinear characteristic of the vessel wall itself. So, let me introduce you to pulse wave velocity, the velocity with which the arterial pulse wave travels from point A in your arterial system to point B. Now, the pulse wave velocity preserves the nonlinear characteristics of your vessel wall. So, like you might recall, you have a low BP level and your high BP level, say 80 mmHg to 180 mmHg within one heartbeat. So, the pulse wave velocity takes typical values somewhere from 3 meter per second to 5 meter per second, varying nonlinearly within one heartbeat from your low BP level to high BP level, preserving the nonlinear characteristics of the vessel wall. Now, therefore, the increase in vessel wall stiffness gets manifested as an increase in the pulse wave velocity. Now, to give you some numbers, if you are very young, you will have the pulse wave velocities varying in the range of 2 to 4, and it keeps increasing all the way to almost up to 10 meter per second as we grow old towards around 50 and 60. So, this is almost the range of values on physiologically possible variations in the pulse wave velocity, all the way from 2 to somewhere around 10 meter per second. So, now that you know that you need to measure the arterial pulse wave and perhaps even measure the arterial pulse wave velocity, which artery to choose from. So, on my right you can see is the actual description of how your cardiovascular system looks like. Now, what I have highlighted is a bunch of arteries called central arteries. Now, central arteries are nothing but the aorta, which is the largest artery, and its main direct branches. So, in the neck region, it accounts for what we call as the carotid artery, and to some extent it involves the femoral arteries in your thighs. So, this whole bunch is called central arteries. Now, why central artery is important? Because the blood pressure in your body varies throughout the arterial network. The blood pressure at your finger is different, from your radial artery is different, from left upper arm is different, from aorta is different. Now, the central blood pressure is the pressure that is getting applied on the heart and almost all of your vital organs, which includes lungs, your stomach, and even to some extent even the brain. And the central blood pressure has superior diagnostic accuracy over the conventionally measured blood pressure that is taken from the arm, which is useful for therapeutic goals of hypertension and even predicting the early onset of hypertension and even vascular aging. So, therefore, our measurement site we have selected as common carotid artery. Now, common carotid artery qualifies all these qualifiers of the central artery, plus it has an anatomical advantage that you have a lot of space around your neck region where you can keep non-invasive sensing modalities. Now, how to measure the pulse wave velocity? First, you need an instrument to record the arterial pulse waves itself. So, here you can see a developed instrument by me which composes of multiple sensors. I want your attention to go to the extreme ends, which are two ultrasound sensors. I am calling it as distal and proximal. Now, the ultrasound sensor sends out the mechanical waves and it captures the compression depression patterns of your blood vessel, translating into diameter waveforms from both proximal side and distal side, separated by non-distance. And in the middle I have a highly sensitive pressure sensor which can capture the skin surface vibrations. Now, this is how the schematic will look like of the probe with respect to the location of the artery and how it is getting positioned on an actual participant. Now that you have an instrument, you need a method to determine the pulse velocity, and the most direct approach to measure the pulse velocity is to tap out two signals simultaneously together from the traveling pulse wave along the artery with non-distance between them. Let us call one as the proximal and other as the distal. Once you have this information, what we can look at is the time difference, the temporal difference, phase delay between these two measured waveforms, and measure the pulse transit time, that is the time delay. Once you have the time delay, using the basic distance prime formula, you can arrive at what is the velocity. I want your attention to the fact that this time delay is not a constant number, but a number that is going to vary non-linearly within the valley to peak in line with the expected non-linearity of the vessel wall itself. But at least this is what we are expecting. Now, in reality, what happens when you do collect measurement data of these proximal and distal pulse waveforms, say from carotid artery, what we observe is called that we observe a crossover between the waveforms, especially somewhere from the mean level towards the systolic peak. And we initially thought this could be a measurement issue, but later when we redid the experiments in an actual animal, anesthetized animal, using standard equipments, standard pressure catheters that are having sensors that are separated by non-distances, we observed a very similar kind of crossing over between your proximal and distal pulse waveforms, corrupting the measurement of pulse velocity. Now, especially at the crossover point, if you can calculate what is the time delay, it's almost coming to zero. That translates mathematically to infinite pulse velocities, which physiologically itself is not possible. I was mentioning the upper limit of around 10 meters per second. That's what we are expecting. So, now I want to rephrase the question, how to measure the pulse wave velocity, this time more reliably. I need a biophysics framework, first of all, to explain what's going on, and then only I can have means of correcting them. I want to introduce you to the concept of pulse wave reflections. So, as the left ventricle ejects a forward moving pulse wave, it encounters a so-called reflection sites. It includes the branching of arteries, which sends back another wave, reflected wave, and it superimposes back with the next pulse wave. Now, together it produces what we are actually measuring as the pulse wave. So, the measured pulse wave is now a superposition of a forward moving wave and the reflected waves together, and there is no way you can measure them separately. Now, we have a traveling pulse wave, not just in the positive direction, but now in the reverse direction as well. Now, let's come back to the expectation versus reality situation. What we have here, at this point, we have formulated a hypothesis which is backed by experimental evidence and literature support that wave reflections could be corrupting the reliability of measuring pulse wave velocity. If we could remove the effects of wave reflections from the measured pulse wave, perhaps something like tap out the signal together, and if we can only get the forward moving pulse waves, can we improve the reliability of measuring pulse wave velocity and then apply back the original distance time formula. Now, this got me thinking whether this problem is solved somewhere else. So, this is where blood flow in artery means transmission line circuit theory. The blood flow in artery is characterized normally by the Navier-Stokes equation. In its linearized form, as you can see over here, connects the flow pressure to its compliance, leakage flow in the radial direction, inertance of the blood, viscous resistance of the flow. On the transmission line circuit theory, I have the telegraph's equations, which connects the differential equations or connects the voltage and current, and with the voltage and current with the capacitance, conductance, resistance, and inductance per unit length. And the transmission line circuit theory has a well-described mathematical framework that explains the forward and backward moving current and voltages. It has the concept of characteristic impedance and the idea that the impedance mismatches causing reflection. So, I will have well-defined mathematical framework to have equations of what is a forward moving current or a forward moving voltage. So, by analogy with voltage to pressure and current to flow. And I am able to now explain the two important phenomena, that is the forward and backward wave propagation and impedance mismatch causing reflections. So, I have now a biophysics framework to explain what is going on and perhaps a means even to correct it. Now, I want to introduce you the theory of wave separation analysis. Now, if you have your pressure and your flow waveform, which is nothing but your current and voltage, converting them into its frequency domain components, I can characterize what is known as the impedance spectrum, which includes both phase and magnitude. From the impedance spectrum, I estimate what is called as the characteristic impedance of the blood vessels, and using expressions, the final expressions that you can see over there, which is nothing but in terms of pressure and voltage, I have just converted them into the into pressure and flow from voltage and current. So, I arrive at expressions of forward and backward current. So, in order to separate forward and backward current, you need pressure, flow, and an estimate of characteristic impedance. Now, coming to the practical challenges of doing this practically, of course, one, you need a carotid pulse waveform, be it using a high sensitive calibrated pressure sensor or the diameter waveforms as I collected. Second, you need to have a measure of flow, which is conventionally done using Doppler ultrasonography that requires a expensive ultrasonic equipment and perhaps even a trained operator every time you take the device to the field. Now, this puts a constraint. Either you have to have special arrangements on integrating these two systems together, and in no way it's possible to take an ultrasound machine outside of a hospital. So, there is a need for wave separation analysis using single pulse waveform. Say, if you only have your pressure, can I still do the wave separation analysis? So, this reduces the instrumentation complexity, the bypass the need for a hospital setting, scale up to large scale studies, and even benefit to the existing data set that doesn't have the flow. So, this comes to the last point, how to measure the pulse wave velocity reliably, make it easy to measure. Now, for wave separation analysis from single pulse waveforms. So, I told initially that you need to have both pressure and flow to perform the wave separation. Now, in the absence of flow, how can you get back the flow? You can either model the flow or use signal processing techniques to remove the effects of wave reflections and then get back your forward and backward pulse waves. Now, the modeling flow techniques, we have a couple of techniques that I have developed, the multi-Gaussian decomposition model as well as the multi-Rayleigh flow model. Both are techniques that actually recreates the shape of a carotid flow as physiologically as possible to what is there in reality, using only information that is collected from characteristic features of your pressure waveform. So, these are two modeling approaches that I have developed, and currently I am also working on a signal processing approach using substrate analysis. It is a borrowed concept from speech signal processing, and either of these approaches we can use to actually separate out the forward and backward waves without the actual need of the flow measurement. So, let us take a couple of results from the recent studies that we have conducted. So, this is a study conducted on an anesthetized porcine model under drug-induced condition. So, why drug is induced? In order to emulate various blood pressure condition. So, in one experiment, you can have a spectrum of variations in BP that emulate both normotensive and hypertensive situations. And you collect bunch of cycles, say 40 to 50 cycles from your baseline phase and your hypertensive phase in order to perform your analysis. So, in this experiment, we have used standard pressure catheters that are having MEMS sensors that are separated by non-30 mm distances for evaluating the pulse wave velocity. Now, the three different colors here basically distinguishes the three levels that I am finding the pulse velocity, one at the valley level, somewhere in the mean, and somewhere at the systolic level. So, this all happens within one cardiac cycle. Now, in the first half, you can see that the box and whisker shows values of pulse velocity in the ranges of all the way to 10 with a mean value of around close to 30, which is well beyond the level of physiological limits that is actually possible. And you can see we got a coefficient of variation with the measure of repeatability of almost 36% towards the systolic half, although you have a considerable good repeatability at the lower levels. But in the drug-induced phase, which actually emulates hypertension, so hypertension basically means a stiffer vessel, so the reflected waves are traveling more faster into the forward waves, and you can clearly see how the mid regions of the pulse wave is getting corrupted with the larger the poor repeatability measures of 25%. And now when you evaluate the results after performing wave separation, we see that the repeatability measurements are came really good, up to around 7 to 10%, and we are able to recreate back the expected exponential nature that you can see on the right side. Now, a similar experiment was conducted on about 60 human participants, completely non-invasive, where using the probe that I have shown you in the first slide along with the Doppler flow measurements. Now, here we can clearly see the last box and whisker plot is that the pulse velocity variations were well beyond the physiological levels, especially at the peak level, and once we corrected for the reflections using measured flow and flow independent approaches, both were coming almost statistically non-significant mean values in comparison to the theoretical estimates which I have on the first half. So, a quick recap why this is happening: because our biological aging is different from vascular aging. Why? What are we missing? Traditional risk factors fails to predict the cardiovascular disease in time. So, how not to die young? We need to measure pulse velocity reliably. We need an instrument, we need a method, you need a biophysics framework to explain what's going on, and you have to make it easy. So, if we can measure it, we can improve it. Thank you. So, please provide your valuable feedback using the QR code. Thank you. So, yeah, I will just clarify. We are looking at only the arterial system as of now, and within the arterial system itself, the pressure will typically vary from 80 to 120 in one heart cycle. In one heartbeat itself, it's varying. Within the artery, even it varies location to location, but for example, say carotid artery or say brachial artery, which you conventionally measure, your low BP is say 80 mm Hg and high BP is 120 mm Hg, and that happens within one heart cycle. In one heartbeat, that's done. In the next heartbeat, it's again repeating. So, that's why it's a quasi-periodic waveform that eventually that you measure it, and you do that from two different sites simultaneously. You can measure how fast it is moving. Yes, aging is a natural process, and natural wear and tear happens to all your blood vessels. And what we need to rethink is how fast we are accelerating this aging due to maybe our bad lifestyle, unhealthy food, lack of sleep quality, daily stress. All these things are accelerators that will enhance the aging process. If you can track the stiffness of the arteries, in that way you are actually looking at early manifestations of this disease before even the indicators happen in actual blood tests. All right, thank you. Thank you.